Am I audible?
Yes, sir.
Hello?
Yes, sir, you're audible.
Yes, sir.
And the screen?
It's visible, sir.
Okay, fine. Thanks. So, can we start? I explained to you one of the simplest mass analyzers, that is a time of flight mass analyzer yesterday. And part of what we call as the magnetic sector mass analyzer also. What remains of that is what we call as a double focusing mass analyzer. This was a single sector mass analyzer. It is generally single focusing and double focusing mass analyzers. They are called as sector mass analyzers. A single focusing, there is a magnetic sector that separates, and you go on changing the magnetic field, and then different M by Z values will come to the detector and register the current, and you will get a peak. That is how the basic diagram is. The magnetic field deflects, and therefore the ions with different M by Z values will not be able to reach the electrode, which is placed at one particular point. So if you want all of them to reach the point where the electrode is placed, then you have to change the magnetic field so that for a given strength of a magnetic field, the equation which I think showed yesterday is valid, and therefore the particles can reach the electrode. So how is the mass spectrum recorded? What is the way in which you record a mass spectrum? The mass spectrum is recorded usually by changing the magnetic field, and I repeatedly said that the x-axis of the mass spectrum is actually the magnetic field strength, which is converted to M by Z to facilitate what are the mass fragments that are obtained and what is the peak height corresponding to the abundance of those fragments in the given system. So basically what I want to have a look at the equation is this, that the radius of curvature followed by the particles will be r, and this r is equal to, given by this particular expression, m into v upon z into b. I think I had done this yesterday. M stands for mass, v stands for the velocity, z stands for the charge, and b stands for the strength of the magnetic field. So when the velocity is dependent on the electric field strength that is applied, because electric field strength is going to accelerate the charge beam, particles in the charge beam, and that is going to produce the velocity. So ultimately, when you substitute, because what I'm interested in not anything else, but I'm interested, just a minute. So what I'm interested in is the M by Z value, and you can write on your notebooks the basic equations. The equation for R and equation for 1/2 mv square is equal to V into E. V is the applied voltage, E is the charge. So that is equal to 1/2 mv square. So you'll get an expression for V. Substitute that expression for V in the first equation, R equal to mv upon ZB, and get the answer for M by Z. What is the M by Z is the mass to charge ratio, and that is equal to B square, where B is the strength of the magnetic field. R square is the radius of curvature of the path that the particles are going to follow, and 2V, where V is the applied voltage. So what you will get is that M by Z is determined by B and V, because R is going to be fixed. That is the point which I told you yesterday also, that all M by Z values, all fragments in the particle beam, all particles in the beam with different M by Z values, they are going to follow the same path of radius R. That is the point which all of you have to remember. What is going to happen? The different particles with different M by Z values, they have to reach the detector and register the current. Then only that height of the peak will correspond to the, or proportional to the current that is registered. So it is necessary for determination of different M by Z. The particles with those M by Z, they should be able to reach the electrode, get deposited there, and register a current. So they have to follow the same path, and obviously different particles or different m by z cannot follow the same path at the same time. Are you able to follow this point? They have to follow the same path, but they will not be able to do that at the same time. What I mean by the same time? At the same strength of the magnetic field and the electric field. So that is why the fields are changed, so that this equation, what we have to look at is, this is the basic equation, m by z equal to b square r square upon 2v. So when this equation is fulfilled, satisfied, then the particles of that m by z will reach the electrode and they will get discharged over there. When the equation is satisfied that m by z is equal to b square r square upon 2v, r square is going to be fixed, it is going to be constant for a given instrument. So you can make different m by z values reach the electrode by either changing the magnetic field or changing the electric field. And that also I explained to you yesterday, that it is easier to change the electric field as compared to the changes in the magnetic field, because magnetic field is operating over larger distances. The entire path that the particles in the beam are going to follow, that entire path should be covered by the magnetic field, and therefore it is easier to change the electric field applied, and that is what is usually done. It depends on the instrument. In some cases, you have to change the magnetic field. In some cases, you have to change the electric field. That depends on the instrument, but both can be, there are two options available which can be used to get the mass spectrum. So this is the basic feature of a single mass analyzer. In summary, by varying the voltage or the magnetic field of the magnetic sector analyzer, the individual ion beams are separated spatially, and each has a unique radius of curvature according to the mass to charge ratio. That equation m by z equal to b square r square upon 2v. Correct? So I think I have shown all this, that different angles and how it occurs and how it takes place. So now what we want to concentrate on is what is called as a double focusing mass analyzer. Now, what exactly you mean by double focusing, and why is it necessary? A single sector mass analyzer or single focusing mass analyzer is what you are using. In the first case, what we discussed so far was a single sector mass analyzer or single focusing mass analyzer, as it will be called. Now, why is double focusing necessary then? See, in the single focusing mass analyzer also, what you are doing, you are using electric field to accelerate the particles, and then you are using a magnetic field to deflect them. And this works fine because the particles are accelerated, the magnetic field deflects them, and you can make them travel the same path and get to the detector, register the current by changing either the V value or the B value. So it works fine. So why should one go for what is called as a double focusing instrument? Why should one use a mass analyzer, which is a double focusing mass analyzer? And what exactly you mean by double focusing mass analyzer? Single focusing mass analyzer is one where the magnetic field is focusing them onto the electrode and they are getting discharged, that they travel the same path and register the current. That's why it is called as a single focusing. Now, why double focusing is necessary? That is the first point. And that point we will have to first understand and then go for as to how this double focusing is achieved in the sector analyzer. So what we have to understand is that when you take a beam of ions, you are passing them through an electric field, fine. But the beam of ions is accelerated. What you are assuming throughout is that they are accelerated, and that's why they will come to the same energy because the energy input is given. So all of them will reach the same energy because they are accelerated through the same field. And the energy input is common for all ions of different m by z values. That is what we are assuming. And then we are saying that the energy input is equal to 1/2 mv square. And then you say that as the mass changes, the V value will change. That is fine. But what is assumed is that there will be same amount of energy given to all the fragments containing charged particles with different m by z values. This will be true provided you are generating the ions and in the field itself and then accelerating them. Then what is going to happen? Then I will have different fragments with different m by z values, but the amount of energy input is going to be the same. What I want you to understand is that in this particular situation, all the fragments with same m by z will have same velocity. I repeat what I'm saying. Energy input is same. So all of them will get same kinetic energy, but their velocities will differ depending on their mass, right? But if you take up a number of fragments in a given beam, then all those fragments which I got the same m by z value, all of them will have the same velocity v. Other fragments with different m by z value will have a different velocity. But what I want to emphasize and say again and again is that when you take up all the fragments with the same m by z, they should have the same velocity v, because the energy input is same and their velocity is changing only on the basis of their mass. If the mass is more, velocity is less, or vice versa. So if the change in the velocity is only because of their masses, then particles having the same m by z value should possess the same velocity. And that is what is questioned in the double sector mass analyzer. This would be possible provided the ions are being produced in the electric field so that they do not have any initial velocity as such. Are you able to follow this point? If they are produced in the electric field, then they will gain energy the same amount, and therefore their velocities will depend on their mass, and therefore all the fragments of mass having same m by z value, they will be able to have the same velocity. But suppose the ion beam is brought into the electric field. That means originally the ion beam or the fragments in the ion beam with different m by z values have different velocities because they are not subjected to any field. They have been produced and transferred to the electric field. So that is the basic difference between the production of the ions in an electric field and the ions are brought into the electric field from the source where they are generated. So if they are produced in the electric field, then all the fragments with different m by z values will definitely have different velocities, and all the fragments with same m by z values will have same velocity. But when you take up generation of ions at one point and all of them are brought to the electric field for acceleration, when the ions are generated and they are transferred to the electric field for acceleration, it is not necessary that all the ions with the same m by z value will have the same velocity. That is the point which I want to talk about. All m by z will have different velocities. All m by z of the same value would have same velocity provided they are generated in an electric field. But if they are not generated in an electric field and they are brought into an electric field from their source of generation, the electric field will definitely give them the same energy, no doubt about that. All of them will receive the same energy. But initially, they had a kinetic energy, and therefore, such beam of ions, fragments obtained, they will not have the same velocity even if m by z value is same. And for such beams, the double focusing mass spectrometer or sector analyzer is necessary. So what I'm talking about is that the double focusing mass analyzer is needed when you have got mass fragments having the same M by Z value, but not necessarily having the same velocity. And therefore, we say that double focusing will be focusing with respect to direction and focusing with respect to the mass. There are direction means velocity and focusing with respect to the mass. That is why it is called as double focusing. In single sector analyzer, what we are assuming is that all particles having same M by Z will have same velocity because they have been accelerated by the same electric field. So initial velocity is not there. So whatever velocity they gain will depend on the energy supplied and will depend on the mass. So all fragments with same M by Z value will have same velocity. But that may not be the case if the ion source is somewhere else and the ions produced, the particles produced, the fragment produced, which are charged, they are brought into an electric field which will accelerate them, which will impart energy to them. And in that case, you may have different mass fragments having the same M by Z value, but having different velocity. And in such situations or in such cases, it is necessary to focus with respect to velocity and necessary to focus with respect to mass. And that's why it is called as double focusing. One device focuses the beam with respect to velocity. Second device focuses the beam with respect to mass. So because both have been taken care of, the two variables involved, the mass and the velocity, you call it as a double focusing sector analyzer. And this is the situation when the beam of ions produced is brought into the field so that each particle in the beam has got a previous velocity when it is brought into the electric field, and therefore particles with the same M by Z value may not possess the same velocity, and therefore their focusing with respect to velocity is necessary. So in a double focusing mass analyzer, the electric and the magnetic fields are used to deflect the ions, hence the name double focusing. In the sector analyzer, only those ions that possess a particular velocity are allowed to enter the magnetic field. In this case, the electric field allows a narrow beam of ions to enter the magnetic field through a slit. Now, why this differentiation? Because here in the single sector analyzer, with same M by Z value, you expect the fragments to have same velocity. In this case, the value of M by Z may be same, but the velocity may not be same. The electric field applied is curved and that accelerates the ion beam. The magnetic field, as usual, deflects the ion entering it, and the overall mode of operation remains unchanged or it remains the same. This is the basic feature. Actually, it is exactly reverse of what I'm talking about, but we are going to take that point. This sector works in the reverse direction, but what we are going to discuss is exactly opposite. As you can see in the diagram, the ion source is somewhere here. Then the ions are entering the magnetic field. Then they will pass through the slit which is at the center, and then they will enter the electric field and the detector is placed. So they will move only to the detector. What I'm explaining is exactly reverse operation, but still the sector analyzer or the double focusing mass analyzer, the principle remains the same. So here the path traveled is from left to right. You start with the ion source to the left and end up with the detector at the right. What I'm going to discuss is an exactly reverse situation where the ion source is at the right and the detector is placed to the left. The entire operation doesn't change. It's just a matter of convenience whether you first use a magnetic field and then apply the electric field, or whether you first use an electric field and then go to the magnetic field. Because the overall operation, once I explain to you, you will understand that it is almost same. So it doesn't make a difference whether you go from left to right or right to left. So what I'm going to explain it is on the basis of the fact that the ion source is placed to the right. It first enters the electric field and then goes to the magnetic field. The beam of ions first enters the electric field and then goes to the magnetic field. and the detector is placed at the end of the magnetic field, which is easier to explain because all of you are aware in the sector analyzer. The magnetic field distributes the ions, and therefore you can get each ion beam, each M by Z value, reach the focus, reach the electrode by changing the magnetic field. So this is the diagram that I'm going to keep in front of you and then explain how the whole thing starts. You have got an ion source to the extreme right there, and ions are produced. These ions which are produced, they move to the electric field, and the basic important feature of this electric field is that it is curved. It is not a straight two parallel plates through which the electric field is applied. It is applied through two metallic plates, but they are not parallel, they are curved. And that is the main point of first selection or first focusing. How does the first focusing occur? As I told you, in this situation, you may have different fragments moving with different velocities, and even fragments with same M by Z may not possess the same velocity. So when you take up the electric field which is curved and the ion beam enters the electric field, only ions with a particular velocity v will be able to transfer themselves to the chosen path and reach the slit at the center of the diagram. Ions moving with velocities lower than that or higher than that will get deflected more and will reach the walls of the two electrodes. So the point is, what we are assuming here is there is a velocity distribution which is called as the Maxwell-Boltzmann distribution of velocities. All of you are familiar with Maxwell-Boltzmann distribution of velocities. When you take a gas molecules, all the gas molecules move with different velocity, and there is a distribution. There is always a velocity which is called as the most probable velocity, for which the number of molecules having that velocity, that number is highest or that number is maximum. All of you can recollect the Maxwell-Boltzmann distribution of velocities, which is a parabola, inverted parabola. So the same point is assumed here, that the fragments have got different velocities, a distribution of velocities, what is called as the Maxwell-Boltzmann distribution, and therefore even with those fragments which have got same M by Z value may not possess the same velocity. So when you are applying the curved electric field, what happens is the ions with different M by Z values and possessing different velocities. So the situation over here is that we have ions or particles in the beam having different M by Z and having different velocities. Is this clear? So the sorting can be with respect to M by Z, or the sorting can be with respect to velocity. Because there is a velocity distribution, what we call as Maxwell-Boltzmann distribution of velocity. In the earlier case, when you use the single sector analyzer, we had assumed that all particles with the same M by Z are going to possess the same velocity, and different particles with different M by Z will possess different velocity. In this case, the assumption is that even though the particles have same M by Z value, they are not possessing the same velocity. So we have in the system, as the beam enters the electric field, we have in the system ions with different M by Z and ions with different velocities. So it is quite possible that two different particles with different M by Z may be having same velocity. That is one possibility. And the second possibility is two different particles with same M by Z may be having different velocity. So there is a distribution of M by Z in the particle beam, and there is a distribution of velocity. So the first task is to focus with respect to one of these variables. And the first task is to focus with respect to one of these variables is the velocity. How is this achieved? The answer is simple, it's the curved electric field. So the applied voltage and the length of the path of the curved electric field is such that ions with a narrow value of velocity will follow that path irrespective of their m by z value. So what we are doing is, we are doing a selection with respect to velocity. As I said, we are encountering a situation where there is a distribution with respect to mass in the particle beam, and there is a distribution with respect to velocity. That's why I said that you may have particles of the same m by z but different velocities, or you may have particles with same velocity but different m by z values. So the first selection, the first filter is the filter with respect to velocity. So when the ion beam enters the electric field, the arrangement is curved electric field, a definite path to be followed because the ion has to reach the slit at the center. So only the ions having a particular value of V, defined by the strength of the electric field and the radius of the path that is to be followed, they will be able to travel it and reach the slit at the center. Other ions having velocities higher and lower than what you have encountered, they will not be able to take that path. They will either get deflected to the right or they will get deflected to the left. And as they get deflected to the right or the left, they will hit the walls of the electrodes and they will get discharged, or they will not be able to reach the required position, that the slit at the center. So this is selection with respect to velocities. So it's quite possible that when you select a particular velocity, you may have m by z values different for the beam, particles in that selected beam, but their velocities are almost equal. It's a narrow range of velocities that the electric field will allow to go through and enter the slit present in the middle. Is this point clear? So this is focusing. First focusing of the beam is with respect to velocity. So it is a velocity selection, if you may call it, that you are allowing all particles with a particular velocity only to pass through unchanged, undeflected, and reach the slit. All other particles with different velocities may not be able to follow that path, and they may get deflected more than what is required, and therefore they will not be able to reach the slit. So this first focusing is with respect to velocity. What I'm choosing is a narrow beam of particles having a particular velocity range, a small velocity range. Now remember that it is not a single velocity. It is a small velocity range that we are considering. So you'll have particles with a small velocity range entering the slit, and all other particles with different velocity are lost. They are not able to reach the slit. So the beam that enters the slit has almost same velocity and different m by z. And automatically, the magnetic sector will deflect them as per their m by z value. The velocities are almost same. So the deflection will occur as per their m by z values, and the rest of the procedure will same as what you get in the single sector mass analyzer. So first is focusing with respect to velocity, that is electric field doing it, and second is the focusing with respect to m by z, and that is done by the magnetic field. So the only difference between a single focusing and a double focusing mass analyzer is, in the single focusing mass analyzer, the separation or the selection is on the basis of m by z, focusing is on the basis of m by z, because you are having the particles in the beam with the same mass and different velocities. So if we have particles in the single sector analyzer which will have same m by z, and therefore all the particles with the same m by z will have same velocity. Here that is the difference. So I select a particular velocity. So the first focusing in the double focusing mass spectrometer or sector analyzer is going to be the selection with respect to velocity. All the particles which possess a particular velocity, they will be only able to travel this path and reach the slit. All other particles with a higher or lower velocity, they will get deflected and they will not be able to reach the slit as it is. Is this point clear? And then the second focusing is with respect to M by Z, which all of you are familiar with. That the magnetic field is going to deflect, and then you can choose a particular M by Z to come to the focus. What do you mean by come to the focus? Come to the detector, get discharged, and register the current. And this one by one can be done as you do in the single sector analyzer by using the changes in the magnetic field. So that is how the double focusing works. First is the selection of velocities. A particular velocity is selected for particles with different M by Z. And then there is a selection with respect to M by Z, because now the beam that enters the magnetic field is going to possess the same velocity but different M by Z values. So the rest of the procedure is exactly identical to what you do in case of a single focusing mass analyzer. It is called as double focusing because the first focusing is with respect to velocities and the second focusing is with respect to the mass. Okay. The parameter involved are the velocity and hence the kinetic energy or the M by Z value. When the ions are produced, they will have different kinetic energies and hence a distribution of velocities known as the Maxwell-Boltzmann distribution of velocity. So if the ions are produced in the electric field, then only the ions with same M by Z will have same velocity. But if they are not, then the M by Z value may be same, but the velocities may be different for different particles in the beam. The term double focusing is used because the focusing is done both with respect to direction as well as the kinetic energy. So actually the focusing is done with respect to velocity. What I mean by direction is velocity focusing, and what I mean by kinetic energy is the mass focusing. The electric and the magnetic fields are arranged in a proper direction as shown in the figure to choose a well-directed beam into the magnetic field for deflection. That is the most important point. You can underline that word. It is to choose a well-directed beam to the magnetic field for deflection. Well-directed because now the beam moving through the electric field is following a definite path, and that is possible because the electric field is curved. You are using curved plates as the electrodes for the electric field. The beam enters the curved electrostatic field with a DC source. The curved field is produced by means of the use of the curved electrodes that are metallic plates. The effect of the curved electric field is to accelerate the ions, but the curved nature of the electrodes is such that the ions with a particular range of kinetic energy will be able to reach the slit at the end of the electrostatic analyzer. Ions with less kinetic energy and those with more kinetic energy will be meeting the walls of the tube and will thus get eliminated. This is directional focusing achieved or the velocity focusing achieved. So ions with only a particular velocity will be able to follow that path and reach the slit. Since it is a definite directional path followed by the ions, it is called as directional focusing. But actually, this directional focusing is achieved by using what you call as the velocity focusing. You are allowing a particular velocity to move undeflected on that path and reach the slit. Correct? The magnetic field is arranged in such a way that the deflection produces at 90 degrees to the original direction. The collector electrode is located at the focus of the double focus, that is at the end of the magnetic field. The technique of bringing the ions to the focus is same as that used in the sector analyzer. So how you bring different ions in the magnetic field to the focus? By changing it. That is same as a single sector or a single focusing sector analyzer. The length of the electrostatic sector is about 6 inches and that of the deflecting magnetic field is about 4 inches at 90 degrees to the original. So that is how our double focusing mass spectrometer works. Before I go to the quadrupole mass analyzer, I want you to ask questions if you have not followed what has been told. Or if you want, I'll go back and show the diagram of the double focusing magnetic mass analyzer and the screen. Okay, any questions, queries, doubts about this?
Hello, sir.
Yes.
So I had a very basic doubt though. The electrodes which are there, the curved ones, they are supposed to be of the same charge, which has to be opposite to the ions, right?
No, I didn't get your question.
So my question was whether the metal plates which are acting as the electrodes in the electric field are going to be of the opposite charge to that
Yes.
of the ions, but both will be same.
You can apply an electric field. No, so one electrode, they are curved. That is the only difference. The only difference is instead of having two parallel metallic plates acting as two electrodes, positive and negative, you have got them curved. But one electrode will be connected to one terminal, the other electrode will be connected to other terminal. Then only the electric field can be applied. Okay?
Okay, sir. Thank you.
The application is possible only when the two plates are connected to two terminals of the supply, DC supply. And their movement is because of the field. Obviously, what is going to happen? The ion will be tending to move toward that electrode, which is of opposite polarity. It's an electric field, correct? So even though it is curved, the ion will tend to move to the electrode, which is of opposite polarity. But because their velocities are different, that direction in which they are moving toward the opposite electrode, that direction will be different. And therefore, some of them will get reflected more, attracted more to the plate, and therefore they will get deflected to the left, other will get deflected to the right. We are not considering what will happen to when they go to the walls or to the electrode plates. Because what we are interested in is they are not following the required path because of their deflection, and therefore they are eliminated. They are lost. We are not concerned with what happens to them because we are only wanting a particular path to be followed, which will be done by a particular velocity of the particles. Okay?
Yes, thank you.
Anybody else? Okay. So can we start with the quadrupole mass analyzer, which is a very favorite mass analyzer, not only of all the analysts working with the mass spectrometer. It is also a very favorite mass analyzer with respect to the paper setters also, because you will find that there are always more questions on what is a quadrupole mass analyzer and its working than any other type of mass analyzer that you take. Anyway, what is a quadrupole mass analyzer? Why it is called as quadrupole? Quadru means four. Poles means electrodes. So instead of using two electrodes, the mass analyzer is using four electrodes. And that's why it is called as quadrupole mass analyzer. Quadru means four and poles means electrodes. So four electrodes are used, electric field obviously, and therefore it is called as the quadrupole mass analyzer. Now if you are using four electrodes, it is quite obvious that two of them will have same polarity and the other two will have opposite polarity. It is obvious that we have got four electrodes, we cannot have four different polarities. It can be a cathode or it can be an anode. So two electrodes will have same polarity and the other two electrodes will have opposite polarity. So four electrodes are used. That's why quadrupole. Second important feature, I will read that screen afterwards. Listen to what I am talking. The second important feature is, what it says is that quadrupole mass analyzer is functioning as a filter. Its functioning is exactly like the functioning of a filter in an optical instrument. I think I explained this in the beginning. I vaguely remember having done this. So the mass analyzer which we discussed so far, say time of flight mass analyzer, or single focusing sector analyzer, or double focusing sector analyzer, they are mass analyzers which behave like a grating in an optical instrument. What is the difference? When you take up a grating in an optical instrument, what does the grating do? It separates the wavelength, correct? The wavelengths are dispersed. Same way when you take up these mass analyzers, whether it is single sector, double sector, or time of flight mass analyzer, it is behaving like a grating, where the grating deflects and separates the wavelength. Here, the analyzer is separating different M by Z values. So its function is like a grating, correct? Because there is a separation of different M by Z values. Just like in a grating, you have separation of different wavelengths. On the other hand, when you take up the quadrupole mass analyzer, or when you take up the ion trap mass analyzer, their function is like a filter in an optical instrument. What does a filter do in an optical instrument? A filter in an optical instrument allows only a certain wavelength to pass through, and all other wavelengths are destroyed, they are absorbed, they are not able to pass through the filter. So other wavelengths are non-existent, and that is the reason why with the filter you cannot go on adjusting to different wavelengths, because there are no wavelengths available. All other wavelengths are absorbed, and only a particular bunch of wavelengths is allowed to pass through the filter. So the bunch width depends on the quality of the filter. It may be 10 nanometers, it may be 25 nanometers, it may be 30 nanometers, depending on what is the quality of the filter that you're using. But the basic that we are not interested here. What we are interested in is that when you use a filter, it is allowing only a particular set of wavelengths to pass through and destroying all other wavelengths which are reaching it. So what comes out of the filter is going to be a very narrow band of wavelengths, very close value, with the width of the filter wavelength maybe 10 nanometers, 5 nanometers, depending on the quality of the filter. No other wavelengths will be available. Same way, in a quadrupole mass analyzer, what comes out to the detector is obviously one particular M by Z value, and therefore all other M by Z values cannot be reached. So it acts as a filter. It picks up that M by Z value which is reaching the detector. All other M by Z values are lost after deflecting from the path. It is something similar to that what you get if you in the earlier one that we discussed, which was the double focusing sector analyzer. You are using an electric field, and the electric field deflects. Some ions are deflected to the right, some are deflected to the left, and some move straight depending on their velocity. So that's why you call it as velocity focusing or directional focusing. Something similar to that happens in a quadrupole mass analyzer. Only ions with one particular M by Z value, they are able to reach the detector, which is placed at the end of the 4 quadrupoles. So there is a channel through which the ions have to move. And you will find that only ions with a particular M by Z are able to move through that channel undeflected and reach the detector, which is placed at the end. All others are lost because of the deflection, and they will not be able to reach the detector. So it's like a filter. Only one M by Z is allowed and all others are lost. Whereas in sector analyzers or in time of flight analyzers, that the analyzer is dispersing, it is separating different M by Z values, and then you try to reach each M by Z by changing the magnetic field Just like in a grating, the grating separates the wavelength. And if you want to reach a particular wavelength, you have to move the knob so that the slit comes in front of that wavelength and then it goes to the sample. So action is something similar to that. Then how in a quadrupole mass analyzer I will be able to analyze different ions? Are you able to follow this point? I say that it is acting as a filter. And that means only one M by Z value will be able to move through that channel undeflected and reach the electrode, get discharged and register the current. All other M by Zs, they will be completely displaced and they will not be able to reach the detector. So the question is, how is it possible to make other M by Z values reach the detector, register the current, so that you will get the mass spectrum? That is my question. Can anybody answer? You have followed the situation. The situation is simple, that there is a channel between the four electrodes that you are using, two pairs of electrodes that you are using. And through that channel at a time, only one M by Z value ions will be able to get undeflected and reach the electrode. All other M by Zs will not be able to move through the channel. They will get lost in between. And therefore, they will not be able to reach the collector electrode. So collector electrode at a time will receive only one M by Z. Correct? Now, the question is, how will I record the spectrum then with different M by Z values? Have you followed the question? All others are eliminated. Only one M by Z goes to the collector electrode and registers the current. I am not interested in one M by Z. I am interested in the entire mass spectrum, suppose. Then what should I do? I'll come back to this point again, that how the quadrupole mass analyzer is to be used. Quadrupole mass analyzer is extremely useful, provided you are interested only in one M by Z value. Then it becomes extremely useful because it selects that and removes all others. Correct? But suppose I want to record the entire mass spectrum with different M by Z values. How will it be possible is my question. Yes. I want to record the mass spectrum. I am interested in all M by Z values, not only one. Under the given condition, only one M by Z is able to reach the collector electrode through that channel, and then others are lost. But suppose I want all M by Z that are present, how it can be done? This is how it's shown, how it moves. As you can see, there is only one red one which is able to move through. All other ones are deflected. Correct? That is the slit through which it is entering. This is the source. It is moving through that channel which I mentioned, and that is the detector where it is able to register the current. So how will it be possible to use different M by Z to come to the collector electrode is my question. Can anybody answer?
Sir, maybe by varying the potential difference applied, maybe.
Yes, correct. Because see, one M by Z is able to reach the collector electrode by moving through the channel undeflected. And that is possible for that M by Z because the conditions that you are applying. You are applying potential to the four electrodes or the two pairs of electrodes. And if you change that, then it is quite possible that other M by Z under those new conditions will be able to move through the channel and will be able to reach the detector. So what the magnetic sector did in a single sector analyzer, what the magnetic analyzer did, the magnetic field did, the same thing is done over here. Basically, I want all M by Z and I want a mass spectrum. So if only one M by Z is able to reach the collector electrode at a time under the given set of conditions of the electric field, then if I want other M by Zs to reach, there are other M by Z values to move through the channel unchanged and reach the collector electrode, I should be able to change the initial conditions. And what are the initial conditions? The initial conditions are the potential that I'm applying to the two pairs of electrodes, which you call as the quadrupole. So basically, this is how a quadrupole functions. All others are the relevant details as to how it functions. So what I'm going to do, so that's why I said the quadrupole mass analyzer is important, significant, if I am concentrating only on one M by Z value. In that case, this becomes very useful because I don't have to change the settings because I'm interested only in one M by Z. And that M by Z, I can adjust the setting once so that that M by Z goes undeflected through the channel and is able to reach the collector electrode. So I'm not interested in other M by Z values. This becomes an ideal situation. You fix the settings of the potential of the electric field once and for all, and you don't have to change them at all. Every time you do the analysis, you will be able to get analysis for that particular selected M by Z value. So that's what I'm saying. When you are interested in one single peak of the mass spectrum, one particular M by Z value of the mass spectrum, then this becomes a very important mass analyzer, because once you set the conditions, you don't have to bother at all. You don't have to change them at all. Whatever may be the sample, always that particular M by Z will be allowed to move through the channel and go to the collector electrode, get deposited and register the current. So if I want different M by Z, then automatically what I have to do is I have to go on changing the initial conditions, that is the potential applied, and then you will be able to achieve it. So what is the difference there? See, if I have got only one single electric field, static electric field or a DC electric field, it may not be possible for me to control only one M by Z value to reach the collector electrode. It's quite possible that depending on the width of the channel, there may be different M by Z which may remain undeflected as per the width of the channel, pass through the slit and go to the collector electrode, which I don't want to happen. I want only one M by Z to go. And therefore you will find that there is not one single electric field that is applied, as you can see on the diagram on the screen, that there are two potentials that are applied. One is a DC potential and the other one is an alternating radio frequency alternating current. So both these are manipulated to allow a particular M by Z to reach the electrode. So that is the basic functioning of a quadrupole mass analyzer. You cannot do it with a single direct DC potential. That's why you impose two potentials. One is direct current DC potential and the other one is alternating current potential with a definite frequency. So which will mean that with a definite frequency, the alternating current is used. So the polarity for some time period will be 1. For the next half cycle of the AC, the polarity will be different. Is this clear? And the polarity is changing rapidly because we are using a radio frequency AC source. The frequency is in the radio frequency region. So the polarity is going to change rapidly for the AC potential that you are applying. So a combination of AC and DC is utilized in such a way that only one M by Z at a time will be able to reach the electrode, reach the channel and go to the collector electrode at the end. Quadrupole mass analyzer is one of the oldest mass analyzers in use. It is cheap, rugged for operation, so sturdy one. It is more compact as compared to the other mass analyzers, because what you need is only 4 sets of electrodes to be used and then a set of AC and DC circuit. It has a very small scan time of about 100 milliseconds and it is a mass filter rather than mass separator that I already explained to you, that it is a mass filter. It selects a particular M by Z at a time. It is best suited for LCMS systems when you are using one particular M by Z for analysis. It can operate at about 10 raised to minus 5 torr, which is lower than what other mass analyzers operate. Other mass analyzers operate at 10 raised to minus 7 torr or so. So it is about definitely at least 10 to 50 times lower vacuum than what you need for other mass analyzers. And that is important and significant, and that's why you choose it for LCMS, because when you take up an LCMS system, the eluent coming from the LC is at a very high pressure, and interface has to make sure that the pressure reaches the required value of the mass spectrometer. And in that case, this helps because the pressure required for a quadrupole to operate is higher than the pressure at which other mass analyzers are operating. As you can see, it is 10 raised to minus 5 torr, whereas other mass analyzers require a pressure of 10 raised to minus 7 torrs, which is definitely about 50 to 100 times lower than the pressure that you have for quadrupole. And this is significant or important because when you take up an LC, the eluent that comes out of the LC is definitely going to have what you call as a very high pressure, and the interface has to bring that pressure to the pressure of the mass spectrometer. So if the pressure of the mass spectrometer is higher, it is easier for the interface to operate or work. It can routinely measure M by Z values of about 3000. It is best suited for the electrospray ionizer of the biomolecule. That is the next part which we are going to consider. That is what we are going to consider is the analyzers, the ways in which you can ionize an LC and use the different types of interfaces. In the case of a filter used in optical instrument, I will just go through fast because this I already explained. In the case of a filter used in optical instrument, the wanted wavelengths are transmitted and all other wavelengths are eliminated by absorption process. In the case of a grating, the available wavelengths are dispersed and then the required wavelength can be selected from the dispersed wavelength. In the case of the quadrupole mass analyzer, the beam containing those M by Z that travel straight are allowed to pass through. The fragments with other M by Z values reach one of the electrodes and get discharged and thus are no longer affected by the electric or magnetic field. So this acts as a filter. It has four, I think we will stop because this is the description of how it is being brought about, how the quadrupole mass analyzer works, which we'll take up next time. So before we close down, if there are any questions, you are welcome. Yes, any questions?
Sir,
yes.
in the quadrupole mass analyzer, the DC voltage and radio frequency both are applied, and that generates an oscillating electric field. No?
It will definitely create. The total potential may remain constant, or that also will not because it is an oscillating electric field that is used. So it is E0 sine omega t or something like that. The total potential also will fluctuate, and the polarity of the applied AC also will change. That is, the combination of these two is effectively used to keep one M by Z through. We are not discussing the physics of quadrupole. If you have seen, we have got a lot of diagrams afterwards. See. Now, this explains the physics of the quadrupole analyzer, how the two fields, the direct and alternating, are able to select one M by Z. But we are not going into that part because it requires a lot of equations and the relationship with M by Z, the oscillating electric field, the frequency of the oscillating electric field, that is omega. And we don't want to get involved in that because it's, I feel it's a more of physics. Yes. Anything else? Okay. Then we will call it for a day. Next time when we meet, we will start with the working of the quadrupole and then go to what is called as ion trap. Most probably we should be able to complete ion trap working of this and last analyzer, that is Fourier transform ion selected mass analyzer. I think all those I should be able to complete in the next class. So thanks.